When a metallic body is heated, it emits electromagnetic radiation. The radiation may consist of different wavelengths. The electromagnetic radiation may consist of different components having different wavelengths. For example, when the filament of an electric bulb is heated, it emits white light consisting of radiations in the visible range. When this white light is passed through a prism, we obtain a continuous spectrum consisting of all the wavelengths in the spectrum. This spectrum appears as bright lines where one color gradually merges into the other, without a clear demarcation between the adjacent colors. Similarly, when hydrogen gas, which is enclosed in a sealed tube, is heated to high temperatures, it emits radiation. When this radiation is passed through a prism, we obtain the hydrogen spectrum. This spectrum is not a continuous spectrum. It consists of some sharply defined, discrete wavelengths. For example, the spectrum consists of light of wavelengths 6563 angstrom and 4861 angstrom in the visible region. A hydrogen sample also emits radiation with wavelengths greater than those in the visible region. Thus, the spectrum emitted by the hydrogen atom is a discontinuous emission line spectrum as it contains only specific wavelengths of light. When an atomic gas or vapor is excited at a low pressure, by passing electric current through it, it emits radiations containing certain specific wavelengths only. Such a spectrum is called the discontinuous emission line spectrum. The line spectrum is characteristic of the element emitting it. This means that no two elements can give the same line spectrum. Hence, it is also called as the fingerprint spectrum. An emission line spectrum consists of bright lines on a dark background. Now let us again look at the hydrogen spectrum, which was discussed earlier. In the spectrum emitted by the hydrogen atom, the spectral lines can be grouped in separate series. In each series, we observe that separation between successive wavelengths decreases as we go from the higher wavelengths towards the lower wavelengths. Each such set is called a spectral series. An important point to remember is that the wavelengths in each series approach a limiting value known as the series limit. Johann Jacob Balmer was the first to observe such a spectral series. Hence it was named as the Balmer Series. The other such series emitted by hydrogen are namely the Lyman Series, Paschen Series, Brackett Series, and Pfund Series, where each one has been named after its discoverer. Let us look at the lines emitted as part of the Balmer series. The line with largest wavelength in the series is called H alpha, then followed by H beta, H gamma, and so on in the descending order of wavelengths. As the wavelength decreases, the lines appear closer and weaker in intensity. The Balmer series lies in the visible region. Now, let us look at the H alpha line of the Balmer series. Balmer gave a simple empirical formula which these wavelengths follow. If the wavelength of the spectral line emitted is lambda, then 1 by lambda is equal to r into 1 by 2 square minus 1 by n square, where r stands for Rydberg constant, which is equal to 1.097 into 10 power 7 per meter, and n takes integral values 3, 4, 5, and so on up to infinity. This equation is called the Balmer formula. Let this be equation 1. Balmer series can also be written in terms of frequency, nu. We know that velocity of light c is equal to nu lambda. That implies 1 by lambda is equal to nu by c. Substituting this value of 1 by lambda in equation 1, we get nu is equal to rc into 1 by 2 square minus 1 by n square. Substituting n equal to 3 in equation 1, we get 1 by lambda is equal to 1.097 into 10 raised to the power 7 into 1 by 2 square minus 1 by 3 square. This is equal to 1.522 into 10 raised to the power 6. Thus, lambda is equal to 6563 angstrom or 656.3 nanometer. This is the wavelength of the H-alpha line of the Balmer series in the red of the visible region. For the next line of the series, the H-beta line, we have n equal to 4, and for n equal to 5, we obtain the H-gamma line of the series. By putting n equal to infinity, we obtain the limiting wavelength of the series, which is equal to 3646 angstrom or 364.6 nanometer. The limiting wavelength is the shortest wavelength of the series. Now let us look at the Lyman series, which has wavelengths in the ultraviolet region of the spectrum. The presence of ultraviolet wavelengths can be detected by a silver chloride soaked paper, which turns black when exposed to them. The empirical formula for the Lyman series is 1 by lambda is equal to r into 1 by 1 square minus 1 by n square. Here, n is equal to 2, 3, 4, and so on, up to infinity. Let this be equation number 2. Now let us look at the Paschen series. The Paschen series has spectral lines which lie in the infrared region. The formula for the Paschen series is 1 by lambda is equal to r into 1 by 3 square minus 1 by n square. Here, n is equal to 4, 5, 6, and so on, up to infinity. Let this be equation 3. The Brackett series has spectral lines which lie in infrared region. The formula for the Brackett series is 1 by lambda is equal to r into 1 by 4 square minus 1 by n square. Here, n is equal to 5, 6, 7, and so on, up to infinity. Let this be equation 4. The Pfund series has spectral lines which lie in infrared region. The formula for the Pfund series is 1 by lambda is equal to r into 1 by 5 square minus 1 by n square. Here, n is equal to 6, 7, 8, and so on, up to infinity. Let this be equation 5. Spectra of only few elements like hydrogen, singly ionized helium, doubly ionized lithium, etc. can be represented by the simple formulae like equation 1, 2, 3, 4, and 5. Still, these equations are very important as they give the wavelengths that a hydrogen atom radiates or absorbs. When white light passes through a gas and the transmitted light is analyzed, we get a spectrum called absorption spectrum.